Okay, hello. So this is my short video about the Schrödinger equation and sort of how it comes about, or maybe how we can justify this is the equation that we should be looking at. Let me share my screen here. PowerPoint. So last night we talked about experimental results a bunch, and so yeah. We're going to try to justify sort of based on these experimental results that the Schrödinger equation is the right wave equation for quantum particles. So we saw that particles exhibit a wave-like nature, and as such they have a frequency, and the energy is proportional to the frequency by Planck's constant, and I'm using nu for frequency instead of f. So we have E equals hf, or E equals h nu. That's one expression for the energy. And then we also just have from regular old classical mechanics that E equals Ke plus Pe, kinetic energy plus potential energy. And then kinetic energy, right? The classical formula for this, if you have a particle with mass, is the mass times the velocity squared over 2. And then the momentum is P equals mv. And so surely mv squared over 2 equals P squared over m. So the kinetic energy is P squared over 2m, right? That's just totally classical physics. And then we have the potential energy V. And this is going to be the potential. This is what's going to change based on the scenario we're in. And then also by the de Broglie hypothesis, any particle has a momentum that's proportional to its wavelength. So the de Broglie wavelength lambda, I'm sorry, let me fix this really quick because this is the wrong equation, right? The de Broglie wavelength lambda is equal to h times p, where h is Planck's constant. So a particle having a wavelength is the same thing as it having momentum. And then also I'm going to define some constants here just to make things a little bit easier. And the constants, just to remember these constants, maybe you've seen these before, but right, h bar is just h Planck's constant over 2 pi. And then we have this k here is the wave number. So the wave number is basically the same information as the wavelength. K equals 2 pi over lambda. 2 pi over lambda. Okay. And then instead of frequency, instead of nu, we can also use angular frequency. So the angular frequency, I'm going to define here as well. The angular frequency is just 2 pi times the normal frequency, 2 pi nu. So there we have basically we can replace. So obviously knowing the frequency is the same as knowing the angular frequency. So I can in all my equations I can replace nu with omega, the angular frequency. And knowing the momentum is the same as knowing the wavelength by the de Broglie thing. And knowing the wavelength is the same as knowing the wave number, because the wave number is just 2 pi over the wavelength. So I can replace momentum with the wave number in all my equations. Okay, so we're going to do that. When you see nu, or when you see omega, you can think this is the same as having nu. And when you see k, this is the same as p, pretty much, minus some constants. Okay, so since particles exhibit a wave-like nature, we want to write down a wave equation, the solutions to which are going to be the wave functions. So that's what the Schrödinger equation is it's a wave equation, and the solutions are the waves that we're looking at. And they're the waves that the particles sort of behave like. So I'm going to tell you the requirements for a wave equation. the first requirement for a wave equation is that it has to explain superposition. So that means like these experiments where we see that particles exhibit interference and diffraction behaviors, that means we need superposition to explain this, wave superposition. Like if I add two waves, I get another wave, that's another solution to whatever wave equation we have. And this mathematically is the same thing as requiring linearity of your equation. So that means if if psi A is a solution and psi B is a solution to the wave equation, then we need that a linear combination, lambda A psi A plus lambda B psi B should also be a solution. And these lambda A and lambda B, I guess, could be any complex, a complex linear combination. So that's the wave superposition. And then here's the mysterious requirement, is that the wave equation should be built from the wave function and its derivative. And this is maybe a mysterious requirement for now, but we don't really want like a equation that depends on the 10th derivative or something of the wave function. But yeah, basically we want to be able to take the wave function and take derivatives of it with respect to t and x and be able to get the wave equation. And then the rest of this we're going to obtain from thinking about what happens for a free particle. So a free particle is a particle that is that's not under the influence of like an external force or an external like potential. So in quantum mechanics, that means the potential is uniform. That means uniform potential, because right, if the energy is zero, the particle is under the influence of no external energy. But the energy is minus the gradient of the potential. So that means the potential is constant. And as we know about potentials, if the potential is constant, we might as well make it zero, because I can always do a change of coordinates to pick where potential equals zero is. So I might as well pick it at that constant and make the potential constant. So that's that. Then I have the expression for energy, right? Now I have two expressions for the energy. One of them is p squared over 2m plus a constant. That's v is constant. And I might as well make this zero. So just make this zero. So E equals p squared over 2m. That looks like a delta. E equals p squared over 2m. And then we also have E equals h nu from the Einstein thing, the photoelectric effect, everything. E equals h nu. And then I can also rewrite h nu as being h bar omega, because h bar is h over 2 pi and omega is 2 pi nu. Okay, so a free particle should have a well-defined wavelength and a well-defined frequency. And what are the functions with well-defined wavelength and well-defined frequency? Like what are those? Those are sine and cosine waves, right? So those sorts of functions are sine of kx minus omega t and cosine kx minus omega t. These are like traveling plane waves traveling in the x direction. And in general, any function with a well-defined frequency and wavelength is going to be some linear combination of these two sorts of functions. And so just a little aside about the equivalent thing we do in electromagnetism, right? In electromagnetism, you use Maxwell's equations to get the wave equation for electromagnetism. You do like, you look at the Maxwell's equation, and then you take like the curl of E, and then get rid of the divergence term and do all this stuff. And you obtain these two equations, Laplacian of E minus 1 over c squared, second time derivative of E equals 0, and same thing for B. And so this is Maxwell's equations in a vacuum, and so it describes light waves moving at the speed of light, obviously, in a vacuum. And the solutions to this are transverse plane waves, right? They're things that look like the waves are u of xt. equals e to the I kx minus omega t. Or something like this, right? And we get this from Maxwell's equations in a vacuum. But notice that we have, for the wave equation in electrodynamics, we have two space derivatives from the Laplacian and two time derivatives. In quantum mechanics, we're only going to have one time derivative and two space derivatives. So it's a slightly different differential equation that we get. And why? Why do we have a first time derivative and a second space derivative in the Schrödinger equation? Because let's just do an example where psi is a sine wave, right? Let's say psi has a well-defined frequency and wavelength, and there's no cosine part, it's just a sine. Then I take a first derivative, and I get minus psi naught times omega cosine kx minus omega t. So basically I have a omega here. And then if I do a second derivative, I get a k squared. And then if we equate the two expressions for energy, like right here, this is h nu, or the same thing as h omega, right? We need omega on one side of the energy equation. And then on the other side, we have p squared over 2m, and p squared over 2m equals h bar squared k squared over 2m. So on the other side of the equation, we need a k squared, and we get a k squared by doing a second space derivative. Okay, so hopefully that makes sense. Then the equation we need, right? If we want the two expressions for energy to be equal, we need E to equal E, obviously, right? Then we have that some constant times the first time derivative equals some other constant times the second space derivative. All right. So now let's do a fully general sine plus cosine linear combination. I'm going to let a and b be two undetermined constants, right? So a and b are just the components, whatever the components are of this vector type thing. And the exercise that actually, since we're doing this on a video, I'm not going to do it as an exercise. I'm going to just do it. We're going to compute the first time derivative and the second space derivative. And we're going to kind of equate the sine and cosine parts by using sine and cosine as like a sort of basis. And that's another thing we'll justify later, or I'll like sort of half justify it right now. But let's go ahead and let's do the easy part, which is computing these derivatives. So if psi equals a sine, oh my goodness, this writing is terrible. I just have to write very slow. A sine kx minus omega t plus b cosine kx minus omega t. Okay, now I want to compute d psi by dt. Maybe if I turn my video off, it'll write faster. Let's try that. Stop video. Stop video. Okay, try that for a second. Yeah, that helped a little bit. Okay, so if we do a first derivative of sine with respect to t, I get a minus omega a cosine of kx minus omega t. And if I do a time derivative of cosine, I get a minus sign, and then I get another minus sign from the minus omega. So I get plus omega b cosine kx minus omega t. Oh, sorry, sine kx minus omega t. All right. And then now I have to compute the second spatial derivative. So in one dimension, this is d squared psi by dx squared. Now, if I do two derivatives of sine, I get minus sine. And then if I do it with respect to x, I get a k each time. So I have a minus k squared a sine of kx minus omega t. And then I get the same thing, I get a minus k squared b. And then a cosine of kx minus omega t. Okay, and then here's the thing in the exercise. It says use sine and cosine as a basis. So let's justify this. Obviously, if we're looking at things of the form a times sine kx minus omega t plus b times cosine kx minus omega t, sine and this sine and this cosine for the fixed k and the fixed omega span that set of things. So we have to show that it's kind of like that they're sort of linearly independent in some sense, and they're actually orthogonal in some sense because they are a 90-degree phase shift away from one another. And the reason is, right, if I do this inner product, let's do it over a finite length interval. So let's just pick any finite length interval, and I take sine of kx and cosine of kx. Right, that's the sort of inner product where you take the integral of f times the integral of g dx. Since sine is odd and cosine is even, their product is odd. And so if I integrate them over an interval that's symmetric about about x equals 0, right, then the odd and the even parts cancel out. So yeah, right, I have some part over here that's like maybe however much of this is below and above the x-axis is exactly opposite of however much is below and above the x-axis on this side, because it's an odd function and we're integrating it over a symmetric interval. So this integral is automatically 0. And then if I add a phase shift, nothing new happens, right? If I take 1 over L, actually I don't know if 1 over L is the correct normalization constant. You might have to check that. But right, if I take sine of kx minus omega t and cosine kx minus omega t dx, I also get 0, right? So they're sort of orthogonal in this sense. That sort of justifies, we'll talk more about sines and cosines later and orthonormality. But if we use sine and cosine as a basis, then the coefficients of sine and cosine are like the coordinates in that basis, right? So the coordinates of this vector here are, let's say the coefficient of cosine, actually here, what did I do? I think maybe I did up here the coefficient of sine first. So the coefficient of sine is omega, no, I did the coefficient of cosine first. The coefficient of cosine here is minus omega a, and the coefficient of sine is omega b. Right, so we can write this as like a vector in the basis sine, cosine, or cosine, sine. And then if by this equation, beta times this equals alpha times this, right? If I do beta times this, I should get alpha times the other thing. So alpha times the coefficients of sine, which are, the cosine one first, so k squared b minus k squared b and minus k squared a. Okay, so those are the equations we get. And that's basically just from setting this is the thing, the cosine part, and this is the cosine part of this one. So alpha times this one should be beta times this one, and alpha times this one should be beta times this one. That's all we did. And so what we obtain is alpha k squared b equals a beta omega, and minus alpha k squared a equals b beta omega. That's just from equating components of the vector. So then define gamma equals b over a, and then do a little bit of math. You see that beta omega times 1 plus gamma squared equals 0. And then beta omega, right? If omega is 0, then we have no phase, and so this isn't very general. And if beta equals 0, then we're in the case where the second derivative of the wave function is 0, so that's not fully general either. So we're going to say that gamma is plus or minus I, using zero product property. And then by the above thing, beta omega equals plus or minus I alpha k squared. And so we'll choose beta and alpha to satisfy this equation. The thing we should choose is beta equals h bar, and alpha equals minus or plus, from this plus or minus here, minus or plus I h bar squared over 2m. And I hope I didn't switch my alphas and betas here. Let's just check that this is the correct thing. I have been known to switch the alpha and the beta here. Okay, so beta omega, if beta is h bar, then h bar omega should equal plus or minus I k squared times the thing we picked for alpha, which was minus or plus I h bar squared over 2m. Okay, and so then let's see, h bar omega is h nu, which is e, right? So this is h nu, which is e. And this is plus or minus I times minus or plus I is just 1. And then k squared, this equals k squared h bar squared over 2m, which equals p squared over 2m, which equals e. Okay, so these are equal. Okay, so we picked them right. Okay, so now put them into the put them in with the derivatives. So then beta, I put beta here, beta times the time derivative equals alpha times the space derivative, and then solve this, right? And that is the Schrödinger equation for a free particle when potential is 0. So that's what we did. We just solved for the coefficients in the Schrödinger equation. So we're done. For a free particle, we're done. That's the Schrödinger equation for a free particle. And then we generalize, we want to add a potential to this, right? We want to be able to do this also when there's a potential that's influencing the particle that's not uniform. So first we can generalize to 3D, by the way, by just replacing the second space derivative with the Laplacian. So this is the Schrödinger equation for a free particle in 3 dimensions. And then if we want to add a potential, if E is non-zero, all we have to do is add this V times psi term, and you can check that that works. But then when you add a V times psi and V is non-zero, the solutions to this aren't just plane waves. They're not sines and cosines anymore. They're slightly more complicated than that. So that's what we'll do next week is we'll look at, let's pick a potential. We're going to do the particle in a box or infinite square well potential. And we're going to solve this for that potential and see it's not quite just sines and cosines anymore, but it's close. Okay. I think that was all I wanted to say. Hopefully that was maybe a little bit enlightening.